So in this lecture we will start talking about multivariable calculus. Okay, multivariable calculus, and this will be a very rigorous lecture series. We are not going to talk about calculus as we expect in high school, but rather we will be in terms of more rigor as analysis we study, right? So before studying multivariable calculus, we need to have a little bit of sense of what vectors look like and what are linear transformations with respect to vectors. So this is just an overview of these topics. Okay. So throughout we will be working with Rn, which is the, rather let me just define it. So this is the collection of all n tuples xn such that each xi is real for all I equal to 1 to n. Okay. And we usually refer to these elements as vectors. So so this is how we how we refer to it. Then x will obviously admit some form like this, and this is what we often call a row vector. Fine. Okay. Another way of representing this is simply like this. Fine. And sometimes we just omit out this index when it's obviously understandable. And once we have a vector of this form, we can also define something of this sort. Okay, we can define like this, or we can simply use this notation itself. So this will refer to as the transpose of this. Okay, and this is what we call a column vector. Okay. Okay, both of these are equally important because we need to alternately use these notions of row vectors and these notions of column vectors whenever we will be having an equivalent notion of, or rather equivalent use of matrices, when we will be introducing or using the notion of derivatives in case of multivariable case. Fine. Yeah. And the usual so the usual operations in which we define, so we can define an addition and scalar multiplication in Rn component wise, that is, so we can define that if I have ai plus bi, so it will just give me the component, the tuples ai plus bi, and some scalar times ai will give me this. Okay, fine. I guess this is clear, this notation is clear. So let me just use it once and I won't use it anymore. So this means that if I have a1 till an and I add it till b1 till bn, I will get a1 plus b1 and it will continue till an plus bn. And a similar definition can be applied for the column vectors as well. Okay, so similarly for column vectors. Okay, so we are working over Rn, so this scalar typically comes from R. Okay, and yeah, so this is quite good. A more technical term would be to say that Rn over R forms a vector space. So if you have studied linear algebra, you should be pretty much acquainted with this term, right? Fine. So yeah, so what do we we also have that R is a field. So I'm not defining what a field is, but just study it out, at least see the definition of it. That's quite easy to observe. Whatever, the next thing which we require is the notion of a basis, the simplest notion of a basis. This is not as deep as deep you study in case of linear algebra, but this is a very layman definition of a basis. Okay, so given a vector, say x1 x2 till xn, we can write this as x1 times the vector with 1 in the first component and all the other components to be 0, plus 2 into this yeah, sorry, x2 into this plus x3. So we are just adjusting out it in this way, right, making use of our definition of scalar multiplication. Yeah, so I have xn times, yeah, so I have plus xn times 1 in the last component, right, where obviously by the definition of the tuple each xi should be r, should be real for all I. Okay, this collection, so we usually refer to them as symbols because they are very important and are often used. So this is what we call E1, this is what we call E2, this is what we call E3, and inductively enough this is what we call En. So this collection E1, E2 till En is called the standard ordered basis of Rn. Okay, now there are two things to observe here. Why is it called standard? It is called standard simply because, see, when we are in R2 for example, then whenever we choose a point we try to mention it as, suppose say 2 3, right, then this is what we call the coordinate, right, and this coordinate, how do we come up with this coordinate? We first check via the x axis and we see how much distance it has from the origin along the x axis, and it will come out to be 2, and then we go up via the y axis and we check the distance, right. So it carries a specific meaning with respect to its order, right. I cannot write it as 3 2, it will completely change its location on the R2 plane, right. In simple words, so this 2 3, this 2 3 actually refers to as 2 times 1 0 plus 3 times 0 1, where if you have studied vectors in your plus 2 level, you know that this is nothing but the vector I cap and this is nothing but the vector j cap. So this is just the unit vector along the x axis and this is the unit vector along the y axis. In simple sense, since we are talking about an n dimensional space, so let me just give a hint to it. The En refers to the nth, refers to the unit vector along the nth direction, okay, some sort of things like that. So it has to maintain a specific order. I need to have E1 first because E1 corresponds to the first coordinate of the vector we are starting with. These are called coordinates whenever we write it explicitly in this form, and whenever we have a strict sequence of writing it in this way, each of these elements are called the coordinates with respect to the standard basis in very simple sense. So this is the first coordinate, so the E1 vector corresponds to the first coordinate, the E2 vector corresponds to the second coordinate. So this collection needs to have a specific order in which it is written. To see, I can also write this as say E2 first and then E1, that will still form a basis, because by a very simple sense, if you study linear algebra, their basis has in very simple terms, basis has a very a less strong definition when you're just simply talking about basis, but what we actually require is something called an ordered basis. Okay, that's a different topic to talk about. For now, if you study linear algebra, you are easily able to differentiate between why I am using the term ordered. If not, then for the time being you just think of it in this way and you cannot change the order in which E1 E2 till En is written, okay. And geometrically you can think of that E1 corresponds to the first coordinate of the vector we are talking about, E2 corresponds to the second coordinate, so this order has to be strict, and it is called standard because it actually corresponds to the usual way in which a coordinate is plotted, okay, that is why we call it standard. Fine. There can be many other sort of bases in Rn, there can be infinitely many bases in Rn, but those are the things which we not require. We require a strong geometric sense, and for that case the standard basis vectors are what we essentially require. Fine. Okay, and a similar representation can be done in terms of transpose as well. I can take the transpose of x on the left hand side, and then all these will be similarly written as x1 transpose times E1 transpose plus x2 transpose times E2 transpose. In fact, we don't need x1 transpose, I am extremely sorry, because each of these xi's are real, so I need to have E1 transpose, E2 transpose and so on, right. So let me just mention it once. Similarly, I can write x transpose as x1 times E1 transpose continuing till xn times En transpose, right. So yeah, so we will keep on changing these whenever as we require. Okay. The next thing which we need is the notion of a linear transformation. So what is a linear transformation? So it's a mapping between vector spaces which preserves linearity. What do I mean by that? So, and here we are not talking about an arbitrary vector space, we are talking about the Euclidean spaces. So let T be a map from Rn to Rm. We say T is a T is a linear transformation. We say T is a linear transformation if for all x, y in Rn. Yeah, so we are taking elements from Rn. I'm not writing it in coordinate wise every time because we do not require to write it in coordinate in the terms of coordinates every time. But you can just simply think of them to be points from Rn, right? You don't need to think of how their coordinate looks like. It is not required at any cost at this point at least. Yeah, and for all c coming from R, I have T of cx plus y to be c times tx plus ty. Or more specifically, let me add one more scalar here. So for all CD in R, Cx plus dy is C times Tx plus D times dy. Fine. Okay. So what are we typically having? So whenever we are adding two vectors and we are taking their image, so it's like taking the image of each of the vectors first and then adding them up, and taking the scalar multiplication of the image of a vector is same as taking the image of the scalar multiplication of that vector. So we have a linearity in this case, and there are multiple trivial examples. For example, the dilation transformations. The dilation transformations. Yeah. So what do we mean by the dilation transformation? So it's just a transformation of the form Tx equal to Ax for all x coming from Rn, and we can think of T to be a map from Rn to Rn itself. Okay, so these are very well defined dilations. You can, yeah, so this A is a real number. Yeah, you can easily check this. One more thing I need to specify here. Two different dimensional vectors can't be added off. Two different dimensional vectors conventionally are not added. That is, if I have, let's say, 2 3 and I want to add it with 2 3 5, then it's not possible, or conventionally it's not possible. We have not defined it to be possible. Okay, because we do not require such things. Okay. Yeah, so this is a very important sort of an example, and the other example which is also quite important is the notion of projection. Okay, so what is the notion of projection? It's also a very simple case. So we take a linear transformation from a higher dimensional space to a lower dimensional space with, let's say, m greater than equal to n. Okay, or rather let me take specific numbers, then it will be better to understand. Say from R4 to R3, then we can define T of x y z w to be x y z, or yeah, to be x y z. Fine. Okay. Right. So this is what we call the projection of R4 over R3. So this is what we call projection of R4 over R3. Okay. There is also something called what we call an extension, an extension transformation. So what do we, or rather not an extension transformation, a more technical term should be a sort of an inclusion transformation. So let me just add it for simplicity. So I can also inverse this map in this way, such that I take xyz and I can map it to xyz, and the fourth coordinate I make it 0, right? So this is something what we call an inclusion, that including a lower dimensional space inside a higher dimensional space. For example, the simplest example we can talk about is, suppose you have R3, Okay, this is your usual R3 space Z X Y, and this plane, this complete plane, this is what we refer to as the XY plane, right? And this is nothing but your usual R2 plane. Any coordinate you choose out of this plane is of the form XY0. So this is sort of R2 sitting inside R3, right? So this is what we are basically mimicking here. See, everything we study under multivariable calculus, and in fact in case of vector spaces as well, we try to mimic the properties of the usual Euclidean vectors, the two-dimensional or the three-dimensional vectors which we have essentially studied previously. Okay, that's sort of an intuitive idea, right? Yeah, the next thing which we need to specifically talk about is the notion of matrices. All of these things will be required once we dive into the notion of derivatives. Okay, matrices, like yeah, so we have a usual definition. So I'm assuming you know what a matrix is, definition you know, and we know how to add two matrices. What are the condition required? The scalar multiplication of two matrices and the matrix multiplication. These are the things I am assuming you know, so I am not talking about them specifically. What's more important is the following statement, that every linear transformation from some Rn to some Rm can be associated to a matrix of size m cross n. Okay, so this is the statement which is more important. Okay, yeah, let's see why. Rather okay, should we start with an example first and then we see? Yeah, okay, let's see an example first, then we will have an idea. Okay, so example. Okay, so let's say we have a map T from, let's say, R2 to, yeah, let's say we have a map from R3 to R2 by, yeah, so how do we map it? So I have T which takes the vectors, let's say xy. Okay, it's better to write it in column wise, xyz, and it maps it to the following: x1 plus 2x2 plus 3x3 and 4x1 plus 5x2 plus 6x3. Just a simple observation can immediately make you see that this is nothing but 1 2 3 4 5 6 times the vector xyz, right? And here I have a matrix A, and you can easily observe that this matrix is of size 2 cross 3, which corresponds where 2 comes from here, 3 comes from here. So this is the matrix which we say is associated with T. Fine. Now how do we just come up with each of these elements, which you can easily observe that what is yeah, fine, I have this in hand. Okay, so keeping this example in hand, what is the image of the first standard basis vector? So you can easily observe that this is nothing but 1 4, right? 1 4. Yeah, so then what is the second unit vector? So you have 0 1 0, and you can easily see this to be, so it's 2 5, right? It's 2 5. And the third basis vector, yeah, so I can easily see it to be, so I have 0 here, 0 3 6. Now, yeah, again an observation that each of these images are exactly the columns here. Fine, and that's exactly what we do. That's exactly what we do, at least in this case. When you are studying in an arbitrary vector space, they are finding this matrix of a linear transformation. Okay, sorry, it just got inverted a bit. Yeah, so in that case, finding the matrix of a linear transformation is not as trivial as it seems to be in this case. But here, since we are working with just the standard unit vectors, it's easy to find it out. In case of an arbitrary vector space of an arbitrary dimension and arbitrary everything, there it's not as simple as this, but it's a bit different. Fine, fine. Wait a minute. Okay. Yeah. So let's continue the discussion. Yeah. So how do we essentially prove it out? So yeah. So proof that there exists a matrix associated to a linear transformation. Okay, let's check out the proof. Well, the proof is quite simple. Okay, let T be a linear transformation from Rn to Rm, be a linear transformation. Okay, and let E1, E2. So I am using the first brackets just to emphasize that we have an ordered basis till En be the standard ordered basis of Rn. Okay, then consider, so we are just mimicking the example. Consider Tej, the map of each of the standard basis vectors under this transformation. Okay, then this will be some linear combination of the standard basis vectors of Rm, and then this linear combination can be written in terms of a coordinate, right? So it can be written in terms of a coordinate. Let's say A1j, A2j, and so on till Amj, because this is ultimately an element of Rm, so it will take m tuples, right? So I am writing this m tuples in this way. Fine, fine enough. Yeah, then for all x of the form x1, x2 till xn, which is coming from Rn, how do I write Tx? Yeah, Tx is this is a way in which I often refer to as T of x, right? Fine. So this is just T times summation j equals to 1 to n xj ej, right? Yeah, so I can write x as the linear combination in terms of the basis vectors, and where hxi is the respective coordinate. So this is summation j equal to 1 to n. So each of these scalars come out, and I have T of ej here. But how was T of ej written? T of ej was written in terms of the row vector aij, right? So this is nothing but summation j equal to 1 to n xj times aij, where I ranges from 1 to m, right? But then you can easily observe that this is nothing but summation j is equals to 1 to n aij times xj, I is equals to 1 to n, right? I am just multiplying this scalar through the coordinate, right? And then this is nothing but summation j equal to 1 to n aij xj, this I ranges from 1 to m, and then this is, you can easily observe, therefore if I let A to be this matrix A11, A12 till A1n, I have here AM1 till AMn, then this expression is nothing but A times x as a column vector, right? Then I have T of x as A of x, right? Fine. Yeah, because once we fix I to be 1, let's say, once we fix I to be 1, then I have the summation to be A11 x1 times A12 x2 times A13 x3. So I have just where x is considered like this, right? Yeah. So this is the way where we switch row vectors and column vectors as per our purpose. Fine. Yeah, so we have in fact the converse is also very trivially observed, that is if you are given a matrix, so given a matrix A, there exists a linear transformation which we define as LA, such that LA of x is just AX. Fine. So if A is a M cross N matrix, then this linear transformation runs from Rn to Rm, right? Moreover, this matrix is unique. This matrix is unique. Why is it so? Suppose B equals to Bij, so I have here two of the components, right? So I is equals to 1 to M, J is equals to 1 to N, be another matrix associated to T. So I am continuing the proof a bit here, but then T of Ej is Aij, it was already Aij, 1 less than equals to I less than equals to M, and this new matrix also comes into consideration here, right? So they so they are equal at every basis vector, right? Therefore they are equal at every basis vector, hence they are equal at every, or rather from here itself it's clear, right? Which implies that Aij must be equals to Bij for all ij, right? Fine. And which implies that A equals to B. Fine. Okay. So this A is what we call the matrix associated with the linear transformation, or in fact the matrix of the linear transformation as well. Okay. Something which you can also observe and you can prove it, try and prove it yourself. So this is sort of an exercise, that let A M cross N and B N cross B be two matrices. Then if I choose the linear transformation associated to A and I compose it to the linear transformation associated to B, then it will just give me the linear transformation associated with AB. And the converse is also true. That is, if I choose a linear transformation T and I have A to be its matrix, I have a linear transformation say S and B is its matrix, then T composed with S has the matrix AB, right? So you can try and prove it on your own. There is nothing complicated here, very easy to prove. You can try and check it out on your own. Clear? Fine. Okay, so yeah, so let this lecture be up till this much. In the next lecture, we will introduce the notion of derivatives and how we are motivated to define it for several variable case. Yeah, so meet you guys in the next lecture.